joint work with Bartek Klim, Erik Kopczyński, and Szymon Gorunczyk from the University of Warsaw. If you have any questions during my talk, then please interrupt and ask them. Okay, so let me start by giving you some outline of what I will be talking about today. So first I will introduce the kind of problems that we considered, which are constraint satisfaction problems. So I will start with some examples, then I will give you a problem definition, and then I will, so the topic is locally finite CSP, so I will tell you what locally finite means. Then I will move to the main part of my talk, so this is decided, so I will present the result, which is decidability of locally finite CSPs, and I will try to give you an intuition proof, like a sketch proof. Finally, I will talk about complexity of some variant of this problem, and at the end, I will tell you a few words about the connection of this stuff with the theory of the descriptive complexity. Okay, so first, probably the most important notion of this talk, atoms. So whenever I talk about atoms, I just mean elements of some countably infinite set. So we fix some countably infinite set, and the elements of the set I will call atoms. And you can think about the set as a set without any structure. So we can only compare atoms for equality. So there is just equality. Okay, and okay, so some examples of the problems that I will consider today. So imagine that we have an infinite undirected graph. Vertices of this graph are indexed by ordered pairs of distinct atoms. So we have vertices XAB, XAB, and so on. So infinitely many vertices like this. And we put an edge between two vertices if the indices look like this. So if there is an edge between XAB and XBC, where A and C are different. So for every pair of vertices of this form, we have an edge. So here is like a small subgraph of this. So the whole graph is infinite, it's kind of regular, and here is like a small subgraph of this graph. Yeah, is this clear? Okay, so then we ask a question, is this graph three-colorable? So it's kind of clear that it is three-colorable if and only if every finite subgraph of this graph is three-colorable. So this follows from compactness. But then, anyway, we have no clue how big subgraphs we have to check to ensure that it's indeed three-colorable. So it's not clear if this question is decidable. And in fact, this particular graph is not three-colorable. We came up with a subgraph which contains like something about like 20 vertices, maybe a bit less, which is not three-colorable. Okay, so another example, consider an infinite system of linear equations over Z2. So variables are like this thing. So we have variables a variable for every pair of distinct atoms. So XAB, XAB, and so on. Infinitely many variables. And we have two types of equations. The first type of equations is XAB plus XBA equals 1. And this holds for every two atoms AB. So infinitely many equations of this form. And then there is another type of equations, XAB plus XBC plus XCA equals 0. So where ABC are distinct. So infinitely many equations of this form. And once more, we want to know whether this system has a solution. And in fact, this one doesn't. So this is like, so I omitted x's. So those are just the indices. So this is a finite subsystem of this infinite system which does not have a solution. Okay, so those two examples are kind of similar. So we have, in some sense, we have infinitely many variables, and we want to assign to them finitely many values. So now let me give you a slightly different example, which will also fit in general framework that I will introduce today. So now we have a finite graph, finite underrated graph, and we treat atoms as scalars. So now we have, in some sense, we have finitely many variables and infinitely many values. So we want to color this graph with atoms. So atoms are like atoms, we treat them as colors. But we kind of constrain ourselves to, so for every vertex of this graph, we have a set of finitely many possible colors that we want to assign to it. So we fix some constant n, and to each vertex we assign a set of n possible colors. And now we want to know whether we can color this graph with atoms so that no two adjacent vertices share the same color. So this is an instance of this problem, and here is a solution. In this case, there exists a solution. Okay, so this example is indeed very different, because like in the two previous examples, it's not obvious whether this question is decidable. Here, of course, this question is decidable. We just guess an assignment and check whether it satisfies like our condition. Yeah, but this kind of like, we are also in, like, for some reason that I will maybe explain better later, we are also interested in this kind of problems, and like kind of both. So in general, I will consider problems where both we have infinitely many variables and infinitely many possible values, and I will want to decide this most general case. Okay, so now we've seen some examples, so now let me give you a formal definition. So what is constraint satisfaction problem? So an instance of constraint satisfaction problem consists of three things. So we have a set of variables, D, we have a set of their possible values, and we have a set of constraints. So what is a constraint, I will explain in a moment. Like by showing you some example. And we want to find a solution, which is an assignment of values to variables which satisfies all the constraints. So what is the constraint? So let us come back to this was the first example. So we had this infinite graph, and we wanted to check whether this graph is three-colorable. So how can we view this as a CSP instance? So this CSP instance will have, so the set of variables will be vertices of this graph, so we have infinitely many variables. The set of values is the set of possible colors, so let's say 1, 2, 3. And we have constraints, so constraints corresponds to edges. So for each edge, so constraints have a form, a tuple of variables in some relation. So for each edge, like let's say XAB, XBC, there is a constraint. So there is this pair of variables and the relation R, which, like in this case, is just an inequality relation over set 1 to 3. And this says that this pair, this means that this pair of variables can be assigned those pairs of values. So XAB, like this pair, XAB, XBC, in the solution, it has to have values either 1, 2, or 1, 3, or 2, 1, or 2, 3, or 3, 1, or 3, 2. So kind of the assignments 1, 1, 2, 2, and 3, 3 are disallowed because they don't appear in this relation. Okay, so is this clear? So now we can give, so this is a formal definition of a constraint. So a constraint is a pair, a tuple of variables, and n tuple of variables, and NRE relation over the set of possible values. And the constraint means that this tuple, in some sense, means that this tuple of variables can take those tuples of values. Okay, so we have this. So now, what does it mean? So we will consider CSP instances over some templates. So what is a template? So we have a set T of possible values and some relations R1, R2, R3, blah, blah, blah. And we say that, so we fix template like this, and we say that an instance I is over template T if all relations that appear in the constraints are taken, are like with the relations from this structure. So yeah, so we only can have, the relations in the constraints can only be the relations R1, R2, blah blah blah, taken from T. So then the instance is over this template. For example, 3-colorability is over this template with just a single relation, which is the inequality relation over the set 1 to 3. So every instance of 3-colorability can be expressed using this relation. Okay, so the problem that we are interested in is CSP over some fixed template D. An instance of this problem is a CSP instance over this template, and we want to decide whether this instance has a solution. But now, well, I showed you 3 different examples. Like the first 2 are a bit different than the third one. So, what kind of instances and templates do we consider? Okay, so now I will give you an intuition of what a definable set is. I don't want to get into any details here. So we will consider definable instances and templates. So a definable set is, like, for example, as a set of variables of the first 2 instances that we considered. So this set of variables can be defined using first order formula with equality, like you can see here. So the kind of instances and templates that we consider, so here we have the constraints of this instance. The set of constraints of this instance can also be defined using the first order formula over, like, with equality. So yeah, so we will consider instances and templates definable by first order formula. Yeah, which is like a bit more complicated, but well, the intuition is the following. Okay, so they're definable. So like the expressions, the formulas that define them, like, can be written down. So those can be treated as inputs for objects. Okay, and we will only consider locally defined templates, and this definition is easy. So we say that the template is locally finite if every relation in this template is finite. So, okay, so now let us have a look at this. So let us come back to this third example. So yeah, so I want to give you, yeah. So how does the template for this instance look like? For this problem look like? So we have 3 types of constraints, 3 types of relations in constraints. So like, look at the vertices x and z. So if the set that we assign to this vertices have one element in common, then the relation that we get has 3 elements. So we have infinitely many. So in the template we have infinitely many relations of this form, and this kind of relations can be defined by first order formula. So finite and definable. So now we have vertices z and b. So if the 2 sets that we assign to the vertices are disjoint, then the relation that we need in the constraint has 4 tuples. So once more, the relation has finitely many elements, and we have infinitely many relations of this form, which are also definable by first order formula. And finally, if the 2 sets are the same, then we have just 2 tuples in the relation. So once more, the relation is finite. We have infinitely many relations of this form in our template, but once more, there are FO finite. Okay. So more precisely, we fix a definable locally finite template. The problem, like locally finite constraint satisfaction problem, is we fix a definable locally finite template, and the problem that we consider is given a definable instance I over this template, decide whether it has a solution. And the main result that I want to present in this talk is that this problem is indeed decided. Okay, but before moving to this, let me give you an example of one more instance, one more CSP instance, which will be right now it might seem a bit strange, but I will use this particular instance to show you the link between what I'm talking about today and descriptive complexity. So what are linearly p-patch structures? So we fix a finite graph P, just one finite graph P. And then a linearly p-patch structure is a graph. So we have a graph, we cover it with subgraphs called patches. So each vertex and each edge of this graph belongs to some patch. Each patch is isomorphic to P, so we kind of cover this with copies of P, cover this bigger graph with copies of the smaller graph P, and we fix some linear order on these patches. So, for example, if the graph P is just a single edge, then this corresponds to graphs with linear order on the set of edges. So we have a graph, we cover it with edges, like every edge is there, and then we fix some linear order on these edges. And a bit fancy example, so if P is this graph with 3 vertices and 2 edges, then this is an example of linearly p-patch structure. So we have this bigger graph, we cover it with graphs which are isomorphic to this one, and we fix some linear order on the set of those graphs. And the kind of problem that we want to...
So why this linear order? So, I mean, for this cover, so how do you use this linear order?
So this is kind of a part of the structure. So we consider structures which are this order is a part of the structure that we consider. So there's a relation.
Hasn't been used yet. But maybe it will be used in the future.
Yes. So far, but yeah, that's. Okay, so the kind of problem that we are interested in concerning linear p-patch structure is the isomorphism of linear p-patch structures. So yeah, we have this fixed graph, and we are given 2 linearly p-patch structures. With, for convenience, we will see the vertices of these structures as atoms, and we want to know whether those 2 graphs are isomorphic. And this, I will explain this in more detail in the next slide, but this problem can be expressed as an instance of CSP. So, yeah, so we are from those 2 graphs, we construct an instance, and we ask if this instance has a solution, then this corresponds so that the answer corresponds to the answer for the question whether they are isomorphic. And what will be important, all those instances are over some locally finite template, which of course depends on the patch P that we choose at the beginning. Okay, so how do we construct this instance? So we are given 2 linearly p-patch structures, so A and B. Each of the structures is covered with patches. There is this linear order on the set of patches. And the instance that corresponds to, and now we want to know whether those two structures are isomorphic. So the instance that corresponds to this has, so the variables in this instance will be pairs of patches. So there are n variables. The first variable is the pair P1, like the first 2 patches from both structures, and so on. So variables are pairs of corresponding patches. And now, so we want to see this isomorphism as constructed from isomorphism from pairs of corresponding patches. So now the values that we the values are isomorphism between corresponding patches. So we can have an isomorphism between those two, and so on. And the constraints will guarantee that this local isomorphism form a global isomorphism. So variables are pairs of patches. To this pair of patches, we assign an isomorphism from this one to this one, and then a constraint for a pair of variables. So let's say this variable and this variable. And the relation that we have there, it enforces that those two isomorphisms are compatible. So they form an isomorphism of some of those patches and some of those patches. I think that this is written here. Yes. So the relation R says that those two isomorphisms form an isomorphism of some of those patches here and here. So yeah, I hope that this is like not crucial for understanding of this talk, but I hope to move it. Okay. And okay, so and then of course, like in the template, we have all those isomorphisms of corresponding patches, and it's all relations of this form, and this forms a locally finite template for a fixed patch P. Okay, and this template we will use later on to show some connection to this context. Okay, so now we can move to the probably most interesting part of the stuff, well, at least for me. So decidability of locally finite CSPs. And the idea will be to consider kind of regular solutions. So we want to have a solution, so let's consider regular solutions. So what are regular solutions? So consider atom, so by out of A, I will denote the group of all permutations of atoms. And this group acts on the set of, like for example, acts on the set of variables of the first instance. So if we have, so the variables are x, a, b, x, b, c, and blah, 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 so on. So if we have a permutation of atoms, then if we apply this permutation to x, a, b, then we obtain x with index pi of a, pi of b. And this, of course, is once more a variable of this instance. So this means that this group acts on the set. Similarly, this group acts on the set of constraints of this. So this is the instance of, well, whatever. Let's say correlability. So yeah, the first example. So we have constraints of this form, x, a, b, x, b, c, and the relation R. So when we take a permutation of atoms and we apply this permutation to a single constraint, then we get a constraint of this form. And this is once again a constraint which belongs to the set of constraints in this instance.
Something's wrong because the set of constraints was finite at some point, but this now, no.
Every relation
was finite.
Like I'm infinite relation.
Yeah, but then it maps one relation to another relation. So each relation is not invariant under this automorphism.
So the set of constraints doesn't have to be finite, and in this case it's not finite because like for every edge. So this is the set of constraints for the graph coloring.
Yeah.
So there is a constraint for every edge. So there are infinitely many constraints. Just the set of constraints is FO definable. And so this instance is over a locally finite template, which means that every particular relation that we use in the constraints is finite. And it is the case here because the relation R is just so this is just the relation for 3 coloring. So it just uses 1, 2, 3 and it's...
Well, its arity is finite.
No, it has finitely many elements. So this is R here, is the inequality relation over the set 1, 2, 3.
Okay.
So it's finitely many, so it has finitely many elements. But one more important thing, and is that here, so the permutation pi does nothing with 1 to 3. So 1 to 3 are constants. So the permutations only act on atoms. So the relation R here uses, let's say, like whatever, constants 1 to 3. So if we apply this permutation to this constraint, then nothing happens to R, because this permutation does nothing to numbers 1 to 3. Yeah, so we just get, so this corresponds to, so this constraint corresponds to some edge. So here we just get a different edge of this graph, but the relation is the same. It just means that that we cannot have assignments 1, 1, 2, 2, and 3, 3. Okay, so we have this action. So we have this action of permutations of atoms on the set of atoms, and then we can apply those permutations to our variables and to our constraints. And we can also apply permutations to assignments. So if we have an assignment of values to variables, then if we apply a permutation pi to this assignment, then this new assignment assigns value pi of t to the variable pi of x. And the fixed point of this action will be called an invariant assignment. So an assignment is invariant. If we apply pi to this assignment, then we once more get the same assignment. So let us have a look at an example. So consider an infinite system of linear equations. So this one is like simpler. So the variables are the same, are just ordered by distinct pairs of atoms. And we have one type of equations, xab plus xba equals 0. So infinitely many equations of this form. And here we have two different, in fact, solutions to this infinite system of linear equations. So this one is invariant. We just assign 0 to all variables. And this is also a solution, but this one is not invariant. So we assign 0 to all variables except xcd and xdc, and we assign 1 to xcd and xdc. So this solution is not invariant because, for example, if we consider a permutation that maps C to A and D to B, then applying this permutation to this solution will change the solution. Yeah, so in some sense, like all those variables, we can have a permutation that map every variable to every other variable. So in some sense, all those variables are the same, and in an invariant solution, they all have to be assigned the same value.
So here invariant means that it is invariant with respect to all the permutations or just with particular one?
No, with respect to all permutations. So in particular here we have just two invariant assignments. One assignment is assigned 0 to every variable, and the other one assigned 1 to every variable. Because all variables are kind of the same with respect to other permutations. Okay. So there is the following fact. It's not difficult to prove that there are only finitely many assignments. So if we have a definable set of variables and definable set of values, then there are only finitely many invariant assignments, and they can be represented in a finite way, once more using first-order formulas with authority. So because of this, it would be so because of this, for any definable locally finite template T, it is decidable whether given definable instance has an invariant solution, because we can just scan through all invariant assignments and check whether any of those is a solution. So it would be very nice to use this for to decide if a solution exists. But sadly, there are instances that have solutions, but they have no invariant solutions. For example, if we modify slightly the previous system of linear equations, so now we have infinitely many equations of this form, xab plus xba equals 1. So this system, of course, has a solution. We just decide that to assign 0 to, like, for every set of atoms, AB, we just decide that this one, like xab gets 1 and xba gets 0. Then we take CD and we say xcd equals 1 and f of xdc equals 0. And for every pair of atoms, we just make this arbitrary choice, and this forms a solution. But yeah, so we know that there are just two invariant assignments, either assigning 0 to everything or assigning 1 to everything, and none of those invariant assignments is a solution. So there are no invariant solutions to this system of linear equations. Okay, so the idea looked promising, but, well, it doesn't work. So yeah, let's try to fix it. So how do we fix it? Instead of considering invariant solutions, we will now consider monotone invariant solutions. So what does it mean? So we introduce a linear order on the set of atoms. So far atoms were just set without any structure except for equality, and now we introduce a linear order which is isomorphic to the order of rational numbers. And now, so now the group of, like, by this out, I mean monotone permutations. So we have this fixed order, so we can consider those permutations that preserve this order. So this is a subgroup of the previous group, so of course it's, once more, it acts on the set of assignments the same way. And the fixed point of this action we will call a monotone invariant assignment. So once more, so a monotone invariant assignment is like if we obtain a permutation to this assignment, a monotone permutation to this assignment, then it doesn't change it. And the same facts hold for monotone invariant assignments. So there are finitely many monotone invariant assignments, and they can be represented in a finite way using first order formulas, but this time they use the inequality symbol. So also the same fact, for if we have a definable locally finite template, then we can decide whether there is a monotone invariant solution of a definable instance. And this solved the problem, and this is thanks to the theorem of Pestov. So the theorem of Pestov says that every continuous action of the topological group, this one, automorphic of the rational numbers with order, on the compact Hausdorff space has a fixed point. And from this we can deduce that if we have an instance over a definable instance, then it has a solution, if and only if it has a monotone invariant solution. So how do we show this? So we consider the set of all solutions of this instance. Well, it might be empty, but it's so it can be shown that this set is compact, which is the so it's a compact Hausdorff space, and here this is crucial that T is locally finite. So here we use the fact that all the relations are finite, because this is so this fact means that if we have a constraint, then, well, if we have a variable that appears in some constraint, then this variable, because the relation in this constraint is finite, then this variable can take only finitely many values. So, and because of this is a compact space. So the action of this group on this space has a fixed point. So if this set is non-empty, then it contains a monotone invariant solution.